Then we're going to move on to talking about the other type of bonding, which is clearly missed very badly in all my drawings here. Covalent bonding. So unlike, as I mentioned earlier, ionic bonding that we just talked about, covalent bonding is always between two nonmetals. And this is always where we have sharing of electrons. So as I mentioned earlier, and as we will talk about, that sharing of electrons may be equal or it may be unequal sharing, but definitely when you have some type of covalent bond, there is some aspect of sharing of electrons that is happening here. And we'll talk about how we could determine, is it equal sharing or unequal sharing here as we go through it. Gilbert Lewis suggested a role of electrons in chemical bond formation, hence the name Lewis structures, Lewis dot symbols. That's your bonding guy right there. So for example, I'm going to redo this because it got all messed up on PowerPoint here. So we'll fix it here. If we take a hydrogen guy, which has one valence electron, and we add it to another hydrogen that has one valence electron, they are both nonmetals. They clearly both have the exact same periodic trends, which means they both have the exact same feeling of either I want to give away my electrons, keep my electrons. They're identical to each other. So neither one of them is going to want to lay up their electron to somebody else and give it away. So the best that we could hope for, and the best that happens when we get two nonmetals together, because frankly, nonmetals on the periodic table are pretty much sitting in the exact same location, is that they're going to do some type of sharing. So instead of like ionic bonding that we just talked about when we have a metal and a nonmetal, when we have our two nonmetals together, they're just going to agree upon, why don't we just share this? So we're going to share these electrons. The result of that is we get a covalent bond, where in this particular case, there is actually sharing of electrons that are happening. That's also why there is no charges here. There's been no transfer of electrons. These guys have no charges when we're dealing with this type of bonding. So how does this benefit each of them? By sharing electrons. Those electrons that are in the middle count for the hydrogen on the right. And those electrons that are in the middle also count for the hydrogen on the left. So they count for both of them. And that means that technically speaking, by sharing electrons here, each of the hydrogens have two electrons. Yes. Two electrons on periodic table is helium. Helium is a noble gas. If you look on the periodic table, hydrogen's to the left of helium, right? Which means hydrogen, very good take-home message right here. Hydrogen only needs to get to helium to be happy, which means hydrogen should only have two electrons always, which means let me give you some examples of things you should not do as you start drawing. Hydrogen should only be on the outside. It should either look like a one line with hydrogen or two dots on the outside, something to the left of it. If you find yourself drawing hydrogen like this and then putting dots around it, you should put a big X. It's wrong. It should never, ever, ever, one more time, ever have dots. If you feel like the dots were just not scientific enough for you and you needed to lay up like a double bond and the dots, you should put two X's on that because that's even worse. And then my personal favorite, I'm just going to lay down everything I ever learned on this one hydrogen here. I'm going to triple bond it and put lines all over it. No, no, and no. Yes. This is exactly how hydrogen should look. One line with the H, no dots, two dots if you're not going to use lines, because you use lines or dots, as we'll talk about in just a second here. But it should never, ever be surrounded by dots, never, ever double bonded, and never, ever triple bonded. I know it seems maybe logical, but people do it all the time. So again, if you catch yourself doing that, just put the X there yourself. Save me the trouble, right? All right. So we can represent this bonding by either the two dots like we did there, and this is basically what is referred to as a bond, or instead of the two dots, we could use one single line. So one single line represents two dots, which is referred to as a single bond. Now for bonding electrons, which is basically what these are, the electrons involved in a bond, you can use either one that you like. I personally use the lines for anyone that's in a bond like that. But some people like to use the dots. It's not wrong to do it either way. So, but I mostly will draw it with the line. So every time you see a line, it does represent two dots. There's single bonds, double bonds, and triple bonds. So every time you put a line down, it again represents basically two dots that are there. Any questions on that there? So this is basically a covalent bond. And what holds that together is those negatively charged electrons in the middle of those two atoms are going to be attracted to the nucleus of one side and also attracted to the nucleus of the other side. So it feels like a little pulling on both sides, kind of locks the electrons into place and locks the bonds together, that the electrons don't just decide to go away because there's that mutual attraction to the nucleuses of each of the atoms within a bond. So another example would be fluorine. If we look at fluorine, once again, fluorine is group 7 there, and it has 7 valence electrons. So again, here fluorine is a nonmetal. So once again, these guys are going to decide we will share with each other instead of obviously being transferred. Again, you can represent it one of two ways, with the dots that are the electrons between the two atoms, or again the line, and then just use the dots for the other electrons. But once again, if we sort of count up what's happening for each of the fluorines here, the fluorine on the right there now has 2, 4, 6, 8 electrons. And again, those 2 electrons in the middle are being shared. So the fluorine on the left there now has 2, 4, 6, 8 electrons. Once again, lucky number 8 on the periodic table is our noble gases, right? Group 8, basically. And that has 8 valence electrons. So once again here, by sharing of electrons, both of the fluorines are able to achieve that noble gas configuration and end up with 8, which, as you know, hopefully, or will know, bonding 8 is a magical octet number there. Octet rule is basically the goal of everybody to get there, because the goal, again, is to become like the noble gases. Any questions on that there? Now, there are actually different types of electrons, and they're sort of identified by sort of what is happening with those electrons. So let's take a look at that here. All of the electrons here that are represented by dots, these are electrons that are not involved in bonding. I know they're not involved in bonding because, frankly, there is no letter on the other side of the dots. There's nothing there. So they are what are referred to as non-bonding electrons. Most books use non-bonding electrons these days. If you're old and decrepit like me, I use lone pairs, and some people still use lone pairs. So every time I say lone pairs, it is the same as non-bonding electrons. Those are electrons that are not involved in bonding. And again, I think nowadays a lot of books just kind of use non-bonding electrons as sort of the term, but some people still use lone pairs, and they basically mean the exact same thing. They are the electrons that are not involved in bonds. Now, there's also obviously another pair of electrons there that is involved in bonds, and that is that guy right there. And as you might imagine, it also has a very creative name. It is known as bonding electrons. Very creative. I like it. So obviously, bonding electrons are electrons that are involved in a bond. Non-bonding electrons are electrons that are not involved in a bond. And it is only the bonding electrons that you can use the line for usually. Yeah, so you can use the line for the bonding electrons only. And again, if you don't want to use the line, you can still use the dots for the bonding electrons if you prefer. But sometimes the line is good. It really makes you see which ones are being bonded. A lot of times with all the dots, you may get a little lost of where everything is, but you can do either one. You should always show all those electrons when you draw Lewis structures. You should always have the bonding electrons and the non-bonding electrons should be pictured in your picture, actually. So a Lewis structure, again, is a representation of covalent bonding. Here we show the bonding electrons with a line are dots. And again, here we are just showing the valence electrons. Each of these elements have more electrons, those core electrons, but once again, they're not involved in bonding, so obviously they're not pictured. So again, like fluorine, for example, has 7 valence electrons, but 9 total electrons. It has 2 core electrons, again, not involved in bonding and not pictured in a Lewis structure. So if we look at something like water and we draw water here, once again, water actually is sharing some electrons with 2 hydrogens, and I'll do it with all dots so we can see it. So once again, the oxygen in the middle, by sharing electrons with both hydrogens there, now is able to achieve 8 electrons, which allows the oxygen to achieve that noble gas configuration. Each of the hydrogens, by sharing with the oxygen, get 2 electrons, which, as we just talked about, is exactly what hydrogen needs. So everybody here sharing electrons, all 3 elements, the hydrogen, the oxygen, and the other hydrogen, have now all achieved that noble gas configuration, and it's very happy in that way. Just like the fluorine there, each of them are getting 8 electrons really through sharing and reaching that noble gas configuration. Any questions on that there? That brings us to the rule that we've basically been talking about, but officially speaking, the octet rule is the rule that says that basically everybody, again, except for hydrogen, everybody will continue to make bonds until they reach 8 valence electrons around them. As we will talk about, sometimes that just requires a single bond being made. Sometimes it requires a double bond to be made to get everybody to 8, and sometimes it requires a triple bond to get to 8. But we'll talk about when to do that and how to do that as we go through this. And then obviously hydrogen, again, as I think I emphasized enough there, hydrogen should only have 2 electrons. It really should just have 1 line to it, 1 bonding pair of electrons, and never anything more than that. And again, that also means in terms of placement of hydrogen, hydrogen should never find itself in the center of a Lewis structure, because it will definitely end up with way too many bonds to it. So hydrogen should always be on the outside of a Lewis structure. It should never be the center atom of a structure. That is also sometimes referred to the duet rule. And once again, the purpose of that is hydrogen just needs to get over to helium in terms of its electrons, and then it's perfectly fine and happy. So let's talk a little bit about multiple bonds. So we talked about single bonds earlier. So a single bond is represented, like I said, by 1 single line, which means 2 electrons being shared, or a pair of electrons. As I mentioned before, sometimes it requires a double bond to get there, and CO2 is an example of that. Carbon dioxide, the carbon in the middle actually needs to double bond both sides to get itself to 8. That has 4 lines drawn on. Each line is 2 electrons, so 2 times 4 is 8 electrons. The oxygen double bonded there. The 2 lines for the oxygen is 4 electrons, and the 4 dots is 8 electrons around it. Same thing for the other oxygen here. The 2 lines represent 4 electrons, and the 4 dots are the other 4 electrons. Now, all these guys here have hit 8 electrons. Once again, in this case, they had to go to a double bond to do so. Double bond represented by 2 lines, which represents 4 total electrons, or 2 pairs of electrons. And sometimes you do need to go to a triple bond to get yourself to a good situation. And nitrogen, for example, is an example of that. Nitrogen on the right, by actually sharing 6 electrons, or 3 pairs of electrons, gets to 8. And same thing here in a triple bond, 3 lines represented 6 total electrons, or 3 pairs of electrons resemble that. You usually stack the dots if you're doing some type of double or triple bond. You just don't single dot in a line, so that's not a double or a triple bond. So usually you got to stack the electrons if you're going to do that. On the bottom there, the carbon also by triple bonding and sharing with hydrogen gets to 8 electrons, and the hydrogen in each of these each get to 2 electrons by sharing those those electrons with carbon. Should you double bond or triple bond out of the box? The answer is no. And people want to do it because it's like more scientific-y, I think, as well. But we're going to talk about some steps to follow when we draw Lewis structures. And if you draw the Lewis structures following our steps here that we'll talk about, it should lead you to a pretty good structure when it's all said and done. So again, I caution you about a couple of things as we go through in drawing. Don't double bond, triple bond right out of the box. And again, be careful of hydrogen. Yeah. So electronegativity is a really important sort of aspect of sharing electrons. And electronegativity is the ability of an atom to bring electrons towards itself. Right, there we go. Ability of an atom to bring electrons towards itself. Once again, on the periodic table, increases as you go up and right, decreases as you go down, and it is our good friend fluorine that is the most electronegative element you could have. So fluorine is the most electronegative element you could have. So electronegativity really is the thing that determines, when we put two atoms together, will they share those electrons equally or will they share them unequally? So obviously, if we put together two hydrogens, we would expect obviously the hydrogen there on the right and the hydrogen on the left to basically, if my green lines here are electrons being shared, to kind of share the electrons equally between those bonds. Is basically the identical person pulling on those electrons. You can kind of think of it like that, like a rope, right? If you have the identical person on opposite sides of the rope, not much is going to happen, right? The flag, if you're doing like tug of war, is not going to move. Everything's going to be kind of shared equally. There's an equal sort of distribution of the electrons over it. And that's always what will happen whenever you have two elements that are the same and they're sharing electrons, like obviously hydrogen, like also our fluorine that we saw earlier. We would expect these guys once again to basically kind of share the electrons equally. When this occurs and we have equal sharing of electrons, this type of bond is what is referred to as a nonpolar covalent bond. And I'll be honest with you, probably most people just call it a straight up nonpolar bond. So usually somebody will just say nonpolar bond. It is a covalent bond. There's sharing of electrons. There's nice equal sharing of electrons. The result of the equal sharing of electrons is this. There is no like positive side to that bond. There's no negative side of that bond. Everything is distributed equally over it. It's kind of like a neutral bond, if you want to think about it like that. There's like no charge happening. Nice, perfect equal sharing of electrons. In this situation between these two, this would also be considered sometimes referred to as a pure covalent bond, which basically means perfect equal sharing of electrons. This is as perfect equal sharing of electrons as you could get. They both are the same element, so they're going to perfectly equally share those electrons. We will talk about nonpolar bond here in just a second. There's some degrees of equal and unequal sharing of electrons. That's maybe not perfectly equal sharing, but something like this would be perfectly equal sharing and referred to as a nonpolar covalent bond or just a nonpolar bond. Now, what happens if we kind of swap out one of the hydrogens for a fluorine? When we now put our hydrogen and fluorine together, between hydrogen and fluorine, which one is more electronegative? It is fluorine, since it is the most electronegative element we could have. So what that means is the fluorine is going to go, I would like the electrons, thank you very much. And what's going to happen is if this is all the electrons, we're pretty much going to have a majority of the electrons kind of hanging out over there on the fluorine side. Not a lot of electrons still hanging out over there on the hydrogen side. Now, there is a consequence to this. The first consequence is there's definitely unequal sharing of electrons is going to occur here. So this is going to result in unequal sharing of electrons. Also, if I have my HF and all the electrons are hanging out over there on the fluorine side, will the fluorine side be more positive or more negative? So if all the electrons decided to vacation over by fluorine, electrons are what type of charge? Which means if they all just congregated over there by fluorine, the fluorine is going to be a little bit more negative, right? Than the hydrogen, because all the electrons basically moved away, right? So all the hydrogen will be a little bit more positive. So the result of this is it creates a partially negative charge on the fluorine and a partially positive charge on the hydrogen. And that's a delta symbol, basically partially negative and partially positive. It also could be represented by an arrow, which is sometimes referred to as a dipole arrow, where it points to the more negative side, and the back part that makes like a plus sign is to the side that's more positive. That's what it's sometimes referred to as a dipole arrow. This sort of unequal sharing of electrons is another type of covalent bond, and this is what is known as a polar covalent bond, or just a polar bond. Get rid of that so you see it. So this is really a polar bond, or the official name, a polar covalent bond. And again, this is a result basically of the electrons hanging out closer to the fluorine because it's more electronegative. Why is it only a partially positive charge and a partially negative charge? Why is it not like a full positive charge and a full negative charge? In this case, they are still sharing. Yeah, so it may be unequal sharing, but there's some aspect of sharing where it's just like barely hanging on maybe, but it's still hanging on. So those electrons haven't fully moved from the hydrogen to the fluorine. And that's why it's still a covalent bond, because there's sharing, but it's unequal sharing. And that's different than the ionic bond that we talked about, where there is no possibility for sharing. They're just going to give away the electrons, and you get that full transfer of electrons that basically occur. Any questions on that there? So a polar bond is a little bit different, as I mentioned, than even a nonpolar bond. The nonpolar bond is sort of thought of as being neutral. There's no positive side or negative side, but there definitely is a positive side and negative side in a polar bond. And that makes a big difference in terms of how molecules interact if they have these type of bonds, as we'll talk about in future chapters as well. So it does make a big difference in terms of interaction and how certain molecules can interact with one another. There you go. And there's my arrow there. And again, the arrow always points to the more negative side, the one that's more electronegative within the bond, and the one that's more positive has sort of the positive side there. So to summarize the three types of bonding that we talked about, on one end of the extreme, we have an ionic bond, which is between a metal and a non-metal. And we have a transfer of electrons from the metal to the non-metal. That results in our ions being formed, our guys that have charges, our cation and our anion being formed. And once again here, as we talked about, it is that electrostatic attraction that holds that together. No sharing of electrons here. And an example would be like sodium chloride. So again, as soon as you see metal, non-metal, going to be this situation We get full charges occurring here because electrons are fully transferring from one to the other, like the original sort of structures we were drawing at the beginning here today. On the other end of the extreme, we have a non-polar covalent bond, or just a non-polar bond, if you like to call it that. That is between two nonmetals. That is going to be sharing of electrons. That is going to be equal sharing of electrons. And an example would be like our H2 or F2. Those are all examples, obviously, of that. And then sort of in the middle of the two is the polar covalent bond. Also between two nonmetals. Also sharing of electrons. But it is unequal sharing of electrons. And an example would be our guy right here, our HF. That creates, as we just talked about, a side to that bond that's more positive and a side that is more negative. It creates those partially charged parts to that bond. So on this end here, both of these are sharing of electrons. Over here, no sharing. So one end of the extreme, we got like nice, perfect equal sharing of electrons. In the middle, we have not equal sharing of electrons, but not so unequal sharing of electrons that they have transferred with the polar bonds. They're still hanging on, but not really equal at all. And then to the other end of the extreme with the ionic bond, we got a complete transfer of electrons. Nobody's hanging on to their electrons. They are moving from one to the next. Any questions on the three different types of bonding there? What we drew earlier with the Lewis dot symbols was ionic bonding, where we have the transfer of electrons. We will talk shortly here how to draw the covalent bonding with the Lewis structures, where everybody's sharing electrons. Any questions on any of that there? Okay, so how do we know, if we put two things together, whether or not we will actually get equal sharing of electrons, unequal sharing of electrons, an ionic bond? And really one of the main things that we use to help us distinguish that is electronegativity. So as I mentioned before, electronegativity is the ability of an atom to bring electrons towards itself. And it's related to electron affinity and ionization energy. And once again, we are increasing this way with fluorine being the most and decreasing this way as well. So fluorine has high electron affinity, high ionization energy, has high, too many O's there, electronegativity. Sodium is the opposite, it has low electron affinity and low ionization energy, which means, as we talked about earlier, it will give away its electrons pretty easily. And it's not really looking to gain electrons, so it will have low electronegativity. There's a guy by the name of Pauling, and Pauling came up with really a scale of electronegativity that allows you to basically put two elements together and determine whether or not the sharing of those electrons will be equal, will be unequal, or really there will be no sharing of electrons and you'll make an ionic bond. So basically Pauling said he gave values for all the elements from 0 to 4. 4 is the most electronegative. 0, not so much. That sounds scientific. Not so much there. Now, we calculate what is referred to as the change in electronegativity. That's what the delta En stands for, change in electronegativity, by basically subtracting the values for each of the elements in the bond. Like if you had two hydrogens, hydrogen minus hydrogen's value, and hydrogen fluorine, hydrogen minus fluorine's value. And if you do the subtraction and you get anywhere from 0 to 0.4 as the difference when you subtract it, that is considered a nonpolar bond. which is really a covalent bond, a nonpolar covalent bond. If you do the difference and you get above 0.4, which is like 0.5, to below 2, that is considered a polar bond, a polar covalent bond. And if you do the difference and it's above 2, and it's not perfect, this number, by the way, if it's above 2, it's ionic. And really, you don't even need the electronegativity values to determine ionic. All you need to know is I have a metal and a non-metal. It's ionic. You don't even need the numbers. You don't have to subtract anything. You should roll with ionic and be happy that that is the answer, probably. So these are sort of the cutoffs where we can use to determine it. So let's take a look at a table. Let's take a look at maybe this table here. It's got all of them on there. As we can see, as we go from left to right on the periodic table, we see an increase in electronegativity, with fluorine being the most. So for example, let us look at the three things that we just talked about, which was sodium chloride, HF, and we'll do F2. So let's say we wanted to figure out, are these bonds going to share electrons equally, unequally, or not at all sharing? We'll start with our sodium chloride. So sodium's value on the table there is 0.9. Chlorine's value there on the table, if I could see it, is 3. Thank you. So basically here, we're just going to take the larger number minus the smaller, so we get a positive number. So we're going to do the difference in electronegativity will be 3 minus 0.9. That is 2.1, yeah? So 2.1 is above 2, which tells us this is going to be an ionic bond. Once again, for something like this, you don't even need the numbers. As soon as you see sodium and chlorine, metal, non-metal, it's ionic. So if it makes you feel better, you can do that. Not all ionic bonds, when you do electronegativity difference, will get you above 2. There's some that will be less than 2. So again, I would just follow metal, non-metal, ionic, and you'll be okay. Let's take a look at HF. H is 2.1. F is 4. So when we do the difference in electronegativity here, that is 4 minus 2.1. That is 1.9 difference. Our cutoff for 1.9 tells us it is a polar bond, right? Consider the cutoff to go into ionic is above 2. How unequal of sharing of electrons is that? Pretty unequal, yeah. It's pretty much moving. Almost all of them have moved to the fluorine, but they're still hanging in there a little bit. It's very, very unequal sharing of electrons in this case, and that's why it's a polar bond. If we did fluorine and fluorine, that would be 4 and 4, which means our difference in electronegativity, 4 minus 4 is 0. A difference in electronegativity of 0 is a non-polar bond, equal sharing of electrons. So we could use electronegativity values to help us decide how the electrons will be shared. They'll be shared equally or unequally. By the way, when you do get a difference of 0 in terms of electronegativity, that is what I was talking about earlier, is considered a pure covalent bond. That's like your perfect equal sharing of electrons. Why is perfect equal sharing of electrons versus something that has a difference of 0.4? 0.4 is still considered non-polar and is still considered equal sharing of electrons. But really speaking, 0.4 means there's still a little bit of unequal sharing happening there, right? But with a difference of 0, it's perfect equal sharing that occurs. So up to 0.4 is, even though technically up to 0.4 is not perfect sharing, it's still considered enough to be perfect sharing and non-polar. But definitely something of 0 is like perfect equal sharing of electrons. Any questions on that there? Why don't you try some here? Decide, is it ionic? Is it polar? Or is it non-polar? These bonds here, let's do carbon and hydrogen. Let's do potassium and bromine. Let's do carbon and oxygen bond. Let's do sulfur and oxygen. And let us do nitrogen and chlorine. For each of these bonds here, basically use the electronegativity values and determine, is it ionic, is it polar, or is it a non-polar bond? So take a couple. Okay, let's take a look, see how you're doing. So we'll start with we'll do carbon, hydrogen first. Carbon is 2.5, I believe, and hydrogen is 2.1. So again, we're just going to subtract the bigger number from the smaller to get us a positive number, and that's going to be 0.4. So with the difference of 0.4, that is polar, non-polar, ionic. That is non-polar, is really why the cutoff is 0.4, because that's pretty much the bonds we find in organic molecules, and they're non-polar. So that is why it goes up to 0.4 for that particular bond. Let's do KBr. K is 0.8. Br is that 2.8, I think. So our difference in electronegativity here is 2.8 minus 0.8. That is a 2, which will make it ionic. And really, once again here, we did not even need the numbers. Potassium is a metal. Br is a non-metal. So you could just roll with ionic without subtracting, and you would be fine. Let's do carbon oxygen next. So carbon oxygen. Carbon, once again, is 2.5. Oxygen there is 3.5, I believe. 0.5. Once again, difference in electronegativity would be 3.5 minus 2.5. That looks like a 1. That is going to mean carbon oxygen would be a polar bond, where if I drew the little arrow, it should be pointing towards which one? It should be pointing toward the one that's more electronegative, which would be the oxygen. Yeah, so it would be pointing towards that. Oxygen would be more negative in that bond, right? And the carbon there would be more partially positive, as the electrons would be moving towards the oxygen in that particular bond. If I do sulfur and oxygen, oxygen again is 3.5. Sulfur there is 2.5 as well. That is actually going to give me the same difference of 3.5 minus 2.5. Going to give me 1, and also tell me it is polar. Once again, it should be pointing towards the oxygen in this case, right? It is polar. And lastly, we have the NCl one, I believe. Nitrogen is 3. Chlorine is 3. Change in electronegativity here is 0. This is what type of bond? It is a nonpolar bond. It is 2 different elements that actually have the same electronegativity, and that can happen. So for sure, if you have 2 elements that are the same, it's going to be nonpolar, but you can also have 2 elements that are different. The reason for that is what is sometimes referred to as the diagonal rule. And that means that although, what do we do? Nitrogen is further up, chlorine is further to the right, so they cancel out their differences. They're diagonal to each other. Happens in a few places. Carbon and sulfur as well. They're not right below each other. They're kind of like 1 over to cancel each other out. So there's a few that are diagonal to each other that have basically the same electronegativity value. First off, any questions on how to do that there? Yes. You have a similar one, I think. You have the one, I think, a couple of slides back, I think. So you have one in your book as well. I think in your book, they maybe just give you the outside ones maybe and stuff like that. So it would be provided for you if you needed it. Obviously, the values, you just need to know how to use them. Yeah. Now, do you always need the values? The answer is no, you don't always need the values. You could use the general trend in electronegativity to make a pretty educated guess. For example, the carbon and oxygen, they are in the same row here, right? And electronegativity increases to the right, which means because oxygen is further to the right, it is a safe bet that that's going to be a polar bond. with the oxygen being more electronegative. So if you're comparing two things that are in the same row, the guy further to the right will be more electronegative, and that probably will be a polar bond in most cases. In addition, if you look at sulfur and oxygen, they are in the same group. Electronegativity increases up a group, so you can make a pretty safe, educated guess that those two will result in a polar bond, with the one further up in the group being more electronegative. So if you're comparing somebody that's in the same row or the same group, you could just use the general trend, and probably 9 times out of 10, even more than that, you probably will make a correct prediction in terms of electronegativity. So you don't always need the values. You could use the general trend in electronegativity a lot of times to help you make that decision. Any questions on any of that there? Okay. And like I said, obviously these numbers would be provided for you if you needed them and stuff like that. And I think maybe in your book you have maybe something that looks like that, or one of these, I think, yeah. So yeah, sort of, since we really don't do too much with the transition metals, a lot of times they'll cut them out and just kind of give you the sides and stuff like that. By the way, you see the noble gases there have nothing written for electronegativity values. That is because noble gases are happy, yes, and they're stable. So if you ever needed to use a value for noble gas, typically people use 0 because they're not really looking to do much. And that's why there's really no values. And that's why fluorine is the most electronegative atom that we have, because it's the furthest one to the right and up, besides the noble gases, which is next to them. So as we saw, atoms with really different electronegativities tend to form ionic bonds. That's when our metals and nonmetals get together. And atoms with very similar electronegativities will basically settle on sharing the electrons, which is what happens in a covalent bond. Either they'll share equally or they'll share unequally. And that's our breakdown, or to the 0.4, 0.5, and so forth. So let's talk now about the proper steps to follow when you want to draw a Lewis structure for a covalent molecule. And if you follow these steps, you should probably have the right molecule drawn. If you do not follow these steps and decide you want to do what I like to call piecework, which is like I'm going to draw everybody separate with all their valence electrons and try to figure out how they all come together, you'll probably end up with the wrong picture. You'll end up with too many bonds, not enough electrons. That's not the way to do it. If you follow this, this should really lead you to a path of, I probably drew a pretty good picture here. So the first really important thing is to think about logically how everything is arranged together. So to help you decide that, usually in the center of the atom, and most things that we draw here have one thing in the center and everything attached to it. Not always the case, but a lot of times that is the case. The guy in the center should always be the least electronegative atom. So the one in the center should be the least electronegative. That means that we will never find fluorine in the center because it is the most electronegative. And as our conversation earlier today about hydrogen, it will also never be in the center, correct? Never in the center, thank you. It will never be in the center either. So the least electronegative should be in the center. Really, the most important thing that you do is the next thing. You want to count up the total number of valence electrons there are in the entire compound or ion that you're drawing. That number is really important because when your picture is done, you got to have exactly that many electrons, no more, no less. Got to hit it on the nose. If it is an ion that you're drawing, you got to adjust your count for the charge. So if it is something that is positively charged, it has lost electrons. So you got to subtract that off your total. Otherwise, you'll have too many. And if it's something with a negative charge, you need to add it to your total number of valence electrons. So you end up with the correct number of electrons. Once you have done that, you got the logical arrangement. You're going to make one single bond from the center atom to each of the outside atoms. I personally will use lines to do that because they're bonds. Each line represents 2 electrons. So you're going to count up how many electrons you just used when you made the lines, and you're going to subtract off from your total. You will then have some electrons still left. Those electrons go on the outside atoms as dots, pairs of dots, until each of the outside atoms has 8 electrons, except for hydrogen, which you get no dots. And you'll keep filling up all the outside atoms until all the outside atoms have 8 electrons. If you fill up all the outside atoms and they have 8 electrons and you still have electrons to go, then they go to the center atom and you put them on the center atom as dots. So single bond, fill up all the outside atoms with dots. If you still have electrons to go, then to the center atom as pairs of dots. At that point, you should definitely be out of electrons if you put some dots on the central atom. The last thing you want to do is make sure everybody meets the octet rule. And it's this point here that if it does not meet the octet rule, then you need to fix it. And the way we fix it in this class is by making a double bond. If that doesn't fix it, we fix it by making a triple bond. Once again, here, we do not want a double bond or triple bond right out of the box. We want to save that for trying to fix things. So let's do one here together to see how we should do it. NF3. So the first thing I'm going to do here really is I'm going to count up the total number of valence electrons. So nitrogen is group 5, which means it has 5 valence electrons. There are 3 fluorines. Each fluorine is group 7, which means it has 7 valence electrons. That's like 21 and 5. I'm going to go with 26 as my total there. Yeah. Now, between nitrogen and fluorine, the least electronegative is nitrogen. It should go in the center. By the way, if you have a situation like this where you have one element and you got another element that you have 3 atoms of it, usually the one atom's in the middle, everybody else is attached to it. So the logical arrangement, nitrogen in the middle, some fluorine action on the sides. Doesn't matter if I put the fluorine on the bottom or the top. It doesn't. You can do it either way, whichever way you like. It doesn't really matter. All right, I'm going to do one single bond. I'm going to use lines to each of them. 1, 2, and 3. Each of those lines represent 2 electrons. That's 2, 4, 6, 8. Who do we appreciate? That is -6 here. That means I still have 20 electrons that I need to put on my picture. They are going to go on the outside ones until each one has 8 electrons, and they're going on as pairs. So not one at a time, but pairs. So we will do 2, 4, 6. That fills up that guy. 8, 10, 12. That fills up that guy. 14, I think. 16 and 18. That fills up that guy. At this point, I just put another 18 electrons on. I still got 2 more to go. I have nowhere to put it on the outside. Now this is where I will now go to the center atom and put it on as pairs as well, and 2 more there. I have now placed all 26 of my electrons. I want to make sure everybody is okay. And here we go. We have 2, 4, 6, 8 electrons. All the fluorines are exactly the same, so they all have 8. Nitrogen, 2, 4, 6, and 8. So everybody's good. Everybody's got 8 electrons. That would be the proper Lewis structure for NF3. This is all sharing of electrons in this deal. Yeah, everybody's sharing electrons here in this particular molecule. Question on that one there. Let's try one more here before we go. Let's do CO2, CO3, 2 minus. We'll do it together here. So once again here, this is a polyatomic ion. It has a charge. We're going to do the same thing. Carbon has 4 valence electrons, maybe 4. There we go. There are 3 oxygens, each at 6. Now the -2 here, minus means it gained electrons, and 2 is how many it gained, which means I need to add those to my count so that I'm all good. That now gives me 18, 20, 24 valence electrons. Between carbon and oxygen, who should go in the center? Carbon. Once again, oxygen should be around. I'm going to do a single bond from the carbon to the oxygen. I've used up how many electrons there? I've used up 2, 4, 6 electrons. And I wish I had my calculator, but I can go with 18. Hope for the best there. So that is 18 still to go, I think. And at this point, we're going to put those on the outside. So 2 in pairs, maybe 2. Come here. 4, 6. So that is filled. 8, 10, 12. That is filled. 14, 16, and 18. That is filled at this point. That is all 24 electrons. Is everybody good in this picture? The answer is no. Yes. Oxygens have how many electrons around them? Oxygens do have 8. 2, 4, 6, and 8. All the oxygens are identical. 2, 4, 6, 8. 2, 4, 6, 8. How many does carbon have? Yeah, 2, 4, and 6. So this did not meet the octet rule. I need to fix it. So I need to get that guy to 8. Can I just do this and put some dots in there? I cannot, because now how many total electrons do I have? I have 26, which is not 24, no matter how you want it to be 24. It is not 24. So this is a situation where we did not meet the octet rule. We want to fix it actually by trying to make a double bond to try to fix it. In this case, we could actually make the double bond at any oxygen you choose because they're all the same. So I need to make a double bond. Can I double bond the top oxygen and do this? Clearly I can't because I just did it, but should I do it? I should not, for the exact same reason. I now have 26 electrons. My oxygen up on top now has 2, 4, 6, 8, 10. Nice cheer, but way too many electrons for oxygen to have in that case. So when we go to make electrons here, we actually are going to take a pair of electrons and we're going to bring them in to make the double bond. So we're going to pull a pair of electrons in to make the double bond. When we do that, the oxygen on the top will now have a double bond and only 4 dots because I brought 2 in. Everybody else will still have the same as I originally had. And now when we look at it, we can make it all pretty and put a little bracket around it since it has a charge. Now does everybody meet the octet rule? They do. If we look at our oxygen originally, 2, 4, 6, 8. This oxygen, 2, 4, 6, 8. This oxygen, 2, 4, 6, and 8. And now the carbon, 2, 4, 6, and 8. So by making a double bond here, which is when you want to make a double bond, is to fix a problem, not out of the gate. So if by some chance that didn't fix it, I would continue to try to make double bonds by bringing electrons in to do so. If I didn't have anywhere else to make a double bond, I would bring another pair of electrons in to make a triple bond. So it works the same way. If you had to make a triple bond, you bring another pair of electrons in to make that triple bond. By doing that, it maintains our 24 electrons. Everybody has 8 valence electrons around it, and everybody is happy. Any questions on that there? All right.
Okay, so we are kind of picking up where we left off when we were all together. Again, remember, please put here in the chat box for roll. And we're going to pick up in chapter 6, I believe. So we started talking about bonding with everybody here together last time. And we talked about, again, sort of the different types of bonding that we come across. And a reminder that we talk about, there it is, ionic bonding. So ionic bonding is always between a metal and a non-metal. And as we sort of talked about, what we always get in this situation is the metal will pretty much transfer electrons to the non-metal. The result of that is our metal then becomes the cation, which is positively charged, and the anion, which is negatively charged, as a result of the non-metal picking up those electrons. And really one of the major things that you should remember when you think about ionic bonding, and it sometimes confuses people, is there is absolutely no sharing of electrons here. So again, what is holding that ionic bond together is simply the attraction between the positively charged ion and the negatively charged ion. And that is very different than what we get when we have some type of covalent bond that occurs. First off, a covalent bond is between two different things. It's between two nonmetals. And because really they are both nonmetals, they are both going to be pretty much in the same location on the periodic table, which means in terms of their electrons, they really are going to have very similar properties, which means basically overall, nonmetals want to hang on to their electrons. They also want to kind of gain electrons. So when we do put two of them together, really the best that will occur is some type of sharing of electrons. So again, that sharing of electrons here in a covalent bond is a major difference than what we see here in an ionic bond, where there is absolutely no sharing of electrons. Within a covalent bond and within sort of that sharing, the sharing may be equal sharing, which represents a type of covalent bond, which is known as a nonpolar covalent bond. Or really more simply, people just straight up call it a nonpolar bond, kind of leave the covalent part of it out, but they're basically the same thing. Or we may have unequal sharing of electrons. And unequal sharing of those electrons is a result of another type of covalent bond, which is referred to as a polar covalent bond. If I could actually spell there, covalent bond. Or again, in most cases, people really just call this a polar bond. Now, these are really sort of the three types of bonding that we talked about. I guess really non-polar and polar. And really, as we talked about, I think as well, there's sort of an extreme. On one end, we have an ionic bond where we have a complete transfer of electrons from one guy to the next. On the other end of the extreme, we have a non-polar bond where we have nice equal sharing of those electrons. And again, sort of in the middle, we have a polar bond, which is again, not equal sharing of electrons, but not so unequal sharing that the electrons actually transfer. So sort of an intermediate, if you will, in terms of the bonding. We also talked about, and I think where we sort of finished up upon last time when we were all together here in lecture, was what we kind of used to help us determine, would we expect the bond between two atoms to be polar, non-polar, or even ionic? And really the overwhelmingly sort of property that we look at in terms of determining what type of bond that we get is really electronegativity. And if you remember, electronegativity is really the ability of an atom to bring electrons towards itself. And in terms of the periodic table, it increases as we go up and to the right on the periodic table, and it decreases as we go down, with fluorine being the most electronegative element that you could have. And we also saw towards the end there that there was a value sort of given for electronegativity that runs from 0 to 4. And remember that 4, which is pretty much what fluorine has, is the most electronegative you could have. And 0 obviously being not so much, right, in terms of electronegativity. And what we do with these values, if you remember, is we take the difference in electronegativity values. We simply just subtract the two values. And if you subtract the two values that you find on that table, and I think it's just a slide back, we were doing all these things. Again, this is the table we're referring to here of electronegativity values. You simply just take the two values for each of the elements that are involved in the bond, and you basically subtract them. And if you get a difference between 0 to 0.4, that is considered a nonpolar bond. Really, like 0.5 to less than 2 is considered a polar bond. And not perfect, but usually above 2. You can actually have a value less than 2 is still be ionic, but usually above 2 is definitely an ionic bond. And again, when we look at this table, like we did last time here, a couple of things that we talked about, if perhaps you don't have the table available to you, there is a lot of cases where, you don't really actually need the values. So first off, the ionic bond, definitely don't need the values, because if you see one is a metal and the other is a non-metal, it's pretty much going to be an ionic bond. So you don't really even need those values to figure that out. So always, if you see metal, non-metal, ionic, don't really need the electronegativity values. If we are looking at something where the two elements are in the same period on the periodic table, like I think we were looking at carbon and nitrogen, for example, here, and we look at carbon, which is right here, and nitrogen, which is right next door. And because they are in the same period or row on the periodic table, we do know just by the fact of their location that nitrogen should be more electronegative than carbon. And that's enough to tell us it's going to be a polar bond without even needing the numbers. Again, in that situation, we would also know that the arrow, which we typically use to indicate a polar bond, this dipole arrow, remember, points to the side that's more negative, and the other back end that makes like a plus sign is to the side that's more positive. So in this case, it would point to the nitrogen. We also looked at sulfur and oxygen. If we look at sulfur and oxygen, here's oxygen. Sulfur is actually right below it. And what we were talking about last time as well is, again, here, because those two are in the same group, you don't really even need the numbers either. Just the general trend, we see that oxygen is higher up in the group than sulfur. And because they're in the same group, we will know that will lead to an electronegativity difference and definitely a polar bond. So there's a lot of times where you could really make a pretty educated guess in terms of polarity. Is it a polar bond or non-polar bond? By just looking at the general trend on the periodic table. We also talked about a couple of things just to watch out for. There is that sort of diagonal relationship, right, between carbon and sulfur, carbon being higher up, but sulfur being further to the right. So they sort of cancel their contributions and they actually end up with the same electronegativity value. So, as long as you don't have some type of diagonal type of relationship, you might want to look at the values. But if you're in the same row or the same group, you pretty much can make a pretty safe bet that you would have a polar bond. And again, if you have a metal and a non-metal, it's a pretty safe bet that is going to be an ionic bond. Any questions on any of that stuff there we talked about last time? See how you're progressing and kind of help you out probably with maybe where you had to stop. So if we look at this, the first thing we want to do is, again, get the total number of valence electrons. So we know that carbon is group number 4 on the periodic table, which means it's got 4. There are 3 oxygens, which means each oxygen is 6 from group 6. Now, in this particular case, this is carbonate, and it has a -2 charge. So remember that the minus means that it gained electrons, and the 2 is how many electrons it gained. So in this case, we do need to add 2 to our total here, again, because of the -2 charge. Otherwise, you will be short some electrons. And if we do all that, that looks like 18, 20, 24 valence electrons. Again, here, if we kind of look at the periodic table, we see carbon is here, oxygen is here. Carbon is less electronegative than oxygen, and it should be in the center. Again, there's only one carbon and 3 oxygens, so it does make sense to put it in the center. So logical arrangement would be carbon in the center. Again, our 3 oxygens around it. And just like the other one, if you wanted to, you could have put the oxygen on the bottom. It's all good. We are at this point where we're ready to basically make one single bond from the center atom to each of the outside atoms. That is now, each line represents 2 electrons, so 2, 4, 6 electrons we used. If we subtract that from our total, that's a lot of math there. That is 18 more electrons, I think, to go. Those 18 electrons will go on the outside atoms first, again in pairs. So here we go, 2, 4, 6, that is filled, 8, 10, 12, that oxygen is filled, 14, 16, and 18. I have now placed all 24 electrons. The thing that we want to do now is to make sure that everybody has 8 valence electrons around it. If we look at the oxygen, 2, 4, 6, and 8, all the oxygens are identical to it, which means all the oxygens obviously have 8 electrons around it. We can do that without erasing the whole thing here. There we go. Now let's look at the carbon though. When we look at the carbon, it has 2, 4, 6 electrons. It does not have 8. So in this particular case, carbon is not good because it has less than 8 electrons. It has not met the octet rule. So we need to fix that. So can we fix it by putting some electrons there? And hopefully you know the answer is actually no, you cannot do that, because now what happens is we have a grand total of 26 electrons, which is too many. So we can't just add electrons to make it work. So this is the situation where once we place all of our electrons and we still have somebody that has not met the octet rule, we're going to try to fix it. And we're going to try to fix it by making a double bond. In this particular case, you have 3 options. You could double bond oxygen to carbon there, oxygen to carbon there, oxygen to carbon there. I'm going to do the top one. It doesn't really matter which one you choose. They're all the same. Can I just draw a line here to make a double bond? And again, hopefully your answer is no, you should not do that. And you should not do that because of 2 reasons. One, we're back to 26 electrons if we do that. And secondly, this oxygen on top will now have 2, 4, 6, 8, 10 electrons, which are too many. So when we actually make a double bond, what we are actually going to be doing is taking a pair of electrons and basically moving them in to make the double bond. And the result of doing that will give us a structure. If we do it there on top of carbon, we will now move those electrons in to make the double bond. We still have the other 4 electrons there on that oxygen. Absolutely nothing changed on the oxygens on the other side. They remain the same. And to make it look correct and right, since this thing does have a charge, we typically have brackets around it and the charge on the outside. What we have just done is keep a grand total of 24 electrons. So if we look at the electrons total, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. The single bonded oxygen, 2, 4, 6, 8. Single bonded oxygen on the right, 2, 4, 6, 8. Carbon in the middle, 2, 4, 6, 8 with the double bond. Oxygen on top, 2, 4, 6, 8. Everybody has 8 valence electrons, and we have a grand total of 24 electrons, and this would be the correct structure for carbonate. Question on that move there. Now, again, as I mentioned, you absolutely, if you wanted to, could have put the double bond there. And if you did that, you would get another structure that looks like this. The only real difference is double bond to the left. That would then leave this guy as a single bond. And our guy to the right, obviously, as a single bond as well. Again, we'll put a little. You could absolutely have double bonded to the right hand side. And again, the only difference would be that the double bond would end up over here on the right hand side. And single bonded everywhere else. All 3 of these structures are actually related to each other. They're sometimes related by this arrow that heads in both directions. These are what are known as resonance structures. And the reason we have resonance structures is for like really this situation. We could have made the double bond on the left-hand side. We could have made a double bond on top, or we could have made the double bond on the right-hand side. And the real reason for it is the double bond electrons are what are referred to as being delocalized, which means at some point in time, they may find themselves over here. At some other point in time, they may be up there in the middle. At some other point in time, they may actually be over there on the right. So whenever you have really an option like this where you can need to draw a double bond and you have more than one option for where you could put the double bond, you could draw another structure which is just as good and was referred to as a resonance structure. Do you have to draw all the resonance structure every time in a situation like this? The answer is no. If you were asked a question just like this to draw the Lewis structure, you could have drew any one of these 3 structures and they would all be correct. If you were asked to draw all the resonance structures, you should have drawn all 3 of these structures. So you probably won't be asked that in this class, but again, if you're asked just to draw the Lewis structure, any one of these guys would be correct. Any questions on that one there?
The brackets and the negative charge need to be included.
They do. So typically whenever you draw anything that has a charge, which are typically these polyatomic ions, because really polyatomic ions are covalently bonded things like we see here with the carbon and the oxygen sharing electrons, but they happen to have an overall charge. So typically speaking, it's very common practice to put the brackets around it with the charge on the upper right there. And again, for anything that has a charge associated with it.
Okay, thank you.
You're welcome. Other questions? All right, so why don't we try a few more here, make sure. Actually, yeah. Let's go here. Let's do, why don't you take a few moments here and draw the following. Let's do SH2. Let's do CO2. Let's do SO2. Let's do N2. Why not? Let's do NH4 plus. Let's see here. And let's do SO4 2 minus. All right, so take a few moments here, draw a proper Lewis structure for each of these, and we will in a few minutes here or so take a look and see how you did. Again, try to follow those steps. If somebody doesn't meet the octet rule, try to fix it with a double bond. If double bonds don't fix it, try to fix it with a triple bond. They work the same way. You bring the electrons in and see what you come up with. Let's take a look. I know you may not be completely done, but let's see how you're progressing. Make sure everybody's on the right track here. So we'll start with the first one here. So again, we're just going to count up our valence electrons. So sulfur is group 6. There are 2 hydrogens, so that's 2 times 1. That tells us 8 valence electrons. Here, clearly, as we've talked about previously, we never put hydrogen in the middle, so we will go with sulfur in the middle. Hydrogen will be on the outsides. Following the same patterns we've done before, we're going to do a single bond to the center guy, to each of the outside guys. That is 4 electrons that have been used. I then have 4 more electrons to put in there if I subtract that. I am going to put those on the outside ones first, and I'm fairly sure nobody hopefully put any dots on the hydrogens. They are completely full at this point. Remember, hydrogen should not have any dots. That means we then follow our next rule, which is when everybody on the outside is full, we then go to the center and we do place those guys on as dots. So that is 2 and 4. And at this point, we have now placed all 8 of our valence electrons. If we take a look again, hydrogen has 2 on the left, hydrogen has 2 on the right, sulfur in the middle has 2, 4, 6, and 8 electrons with the non-bonding electrons and the bonded electrons, and we have a correct structure. Any questions on that one there? Coming to CO2, again, carbon is group 4. There's 2 oxygens at 6 each. That is 16 valence electrons. Again, looking at the periodic table, we see carbon is further to the left of oxygen. That means it is least electronegative, which means we should place the carbon in the middle, oxygen's on the outside here. We're going to do a single bond to each of our carbons. That is 4 electrons used. We then have 12 more to go on the outside here. So 2, 4, 6, that's filled. 8, 10, and 12, that is filled. We have now placed a grand total of 16 electrons. When you look at this, you should see that the carbon is not good. It does not have 8. It only has 2 and 4 electrons. So we want to try to fix it by making a double bond. You could choose either side here. So remember, when we make that double bond, we're going to bring it in. And when we do that, we will end up with this. And now if we look at the carbon, it has 2, 4, 6 electrons. Better, but not 8. We have an option here to make a second double bond on this guy. And that is what you should do. You should try to exhaust all of your double bond opportunities before you go to triple bond. So in this case, we would then again bring in a pair of electrons on the other side. And when we do that, we will now lay up a double bond on the right to match our double bond we got going on there on the left. And we still have a grand total of 16 electrons. Oxygen on the left and right are the same. It has 2, 4, 6, 8 electrons. Carbon in the middle, 2, 4, 6, 8 electrons. This would be the correct structure for carbon dioxide. Any questions on that there? So again, in a situation like this, if you made a double bond and it kind of helped but didn't fix the problem, but you still have an opportunity to make another double bond, you should do that first before you jump to a triple bond. Any questions on those 2?
Yeah, Professor Ifan, I got a little lost in those 2 lines that you had put for the CO2.
Okay. Making the
on
double
second.
bond?
Yeah.
Okay. So originally, once we placed all of our electrons, we were basically at this guy right here. And the problem with this guy was really the carbon. The carbon ended up at this point with only 2 and 4 electrons. So whenever we place all of our electrons and we need to fix a problem like that, what we need to do is try to make a double bond. So the first thing that I tried was to make a double bond on the left-hand side by bringing these electrons in to make the double bond like we talked about. And at this point, what we end up with is the carbon goes from 4 electrons to now 2, 4, and 6 electrons. It actually got better. It went from like 4 electrons to 6. But remember, the ultimate goal is to get to 8. So instead of on the left-hand side making a triple bond, because we had the opportunity on the right-hand side to make another double bond, that is what we did. So we took those electrons from the outside and brought them in to make another double bond. The result of that now gives the carbon in the center 2, 4, 6, and 8 electrons, which makes it happy. And all of the oxygens also have 2, 4, 6, and 8 electrons. So the goal here, remember, is basically to get to 8 electrons. And sometimes, as we saw in the previous example, it may just take 1 double bond to do it. Sometimes it may take 2 double bonds like we see here. And sometimes you may actually have to go to a triple bond to get everybody to 8. But again, the goal there is to get everybody to 8. And when we make a double bond or a triple bond, we're not adding electrons, but we're actually bringing electrons in to make those bonds.
Okay, got it. Another question.
Yeah.
Our end goal is to get 8. For some reason, my mind is emphasized on 16 instead of 8. Well, why 8?
8 is the octet rule, and really the reason for 8 is if you look at the periodic table. Let me just actually find somewhere to scribble. Go here. If you look at the periodic table, right, group 8 on the periodic table, which is way at the end, that's our noble gases.
Okay.
And noble gases are chemically inert. They are extremely stable. And the goal of all bonding, both ionic bonding, covalent bonding, which is what we're talking about here, is for everybody to end up with the same electron configuration as a noble gas, which means they essentially will end up with 8 valence electrons around them. And that's really why 8 is sort of the magic number. The only one that doesn't need to do that is hydrogen, because if you look on the periodic table, this is hydrogen, which is 1. And just to the right of hydrogen on a noble gas is helium, which is 2. So all hydrogen needs to be happy is just to get to helium. And that's why we say hydrogen should only have 2 electrons, while everybody else needs to get to 8. And really the goal is there to get everybody to the same electron configuration as the noble gases. And that's a super stable situation.
Cool. Thank you.
Welcome.
Professor, I have a question.
Yeah.
So what if it were not to be like the double bonding, but what if we were to put like independent electrons, like 2 on top of C and then 2 on the bottom of C?
No, so you can't really do that. So if you're asking, like, are you asking like if we could just put like electrons here? Is that what you're asking?
Yeah.
You can't really do that because if you just put the electrons, we now have way more than 16. And that number is super important. That is all the electrons you have. So you can't just add electrons to get it to 8, because then you'll end up with too many electrons, more than you should have. So that's why we technically need to use the electrons that we have and bring them in so that more electrons could be shared with the center atom and allow the center atom guy in this case to get to 8. So remember, this number is almost the most important thing when you're drawing these pictures, is that number where you calculate how many electrons you should have, because that is exactly to the nose how many electrons your picture should have. You shouldn't have any more or any less.
Thank you.
You're welcome. Other questions? Okay, so let us take a look at the next one, which is SO2. I have to kind of come this way with it, I think. So sulfur here is 6. Again, here we have 2 oxygens, each at 6. That is 12 and 6, which is 18 valence electrons. Again, this number really important. We got to have 18 total. Again, looking at the periodic table, we see actually oxygen and sulfur in the same group. Sulfur is lower on the periodic table in that group. That means it's the least electronegative, which means we should put sulfur in the middle. Oxygen's on the outside. Again, we want to follow the same pattern here, a single bond and a single bond. So that is 2 and 4 electrons that have been used. So if we subtract it, we're left with 14 more electrons to put on this picture. We will put it on the outside again in pairs. So that is 2, 4, 6. That guy is full. 8, 10, 12. At this particular point, we have placed 16 total electrons. Everybody on the outside is full, but we actually then have 2 more electrons we need to put. Those now go to the center atom, and they are also put on as pairs. So they're put on here as a pair. At this point, we have now placed 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. We're out of electrons at this point. We want to make sure that everybody is okay. And hopefully, if you look at this structure that I'm looking at and I just drew, you will see that the sulfur here is not good. It actually only has 6 electrons on it at this point. Again, 2 on top and 2 and 2 on the left and right hand side. So again, here we can make a double bond to try to fix it. We have oxygen on both sides. We could just try either side you like. We're going to do that because we can't add any more electrons. We need to borrow some from here and basically bring it in to make our double bond. When we do that, our double bond will now end up on the left-hand side. Our sulfur and our oxygen. Now, when we look at it, we still have 18 electrons. The sulfur in the middle has now reached 8. 2, 4, 6, and 8 is now good. And the oxygen on the left there also has 8. And this would be a correct structure for SO2. We also could have, like we talked about with CO3 2-, we could have done the double bond actually on the other side. And you could have drew a resonance structure for that, which would look like pretty identical, except that we double bonded the right-hand side. And again, here we would have 18 electrons and a double bond. If you follow our rules here, you will end up with the correct structure, which does have these non-bonding electrons on the central atom. If you don't follow our thing, our sort of path here, you will probably end up like a lot of people will do on this one, double bond both sides with no dots, and that would be incorrect. So again, sort of the placement of those electrons on the outside ones first, and then the center one is really important to make sure that you do place sort of your non-bonding electrons. Again, these are both resonance structures. You would not have to draw both of them. You could have drew this structure and it would have been fine, or you could have drew the one on the bottom and it also would have been perfectly fine as well. Any questions on that one? All right, then let's take a look at the next one, which is nitrogen. So this one is 2 times 5 for the nitrogens, which is 10 valence electrons. In this particular case, there is no center atom, so there's just 2. So whenever you have 2 atoms, you essentially just place them side by side. And you actually could follow the same rules that we've been doing, which means we'll just connect them both with a single bond. That gives us 2. That leaves us 8 electrons to go. Again, following what we've done before, we will put those 8 electrons on the outside on the right here. 2, 4, 6, it's full. And then the other 8 will go over there. We have now placed all 10 of our electrons. And again, if you're looking at the structure, the way it's drawn, hopefully you could recognize that this nitrogen over here is not in a good position, as it only has 2 and 4 electrons. It is short 4 electrons. So we could try to fix this by doing a double bond. In this case, we really only have one option. We're going to take some electrons in and try a double bond. And if we do that, we end up with this picture here. Again, the nitrogen on the right is all good. It has 8 electrons. Nitrogen on the left, not so good. It got better. It went from, again, 4 here to 6, but it only has 6, 2, 4, 6. So at this point, there is no other option at this point. There's no other way to make a double bond. So now we need to make actually a triple bond. So since a double bond did not fix the problem, we're going to make a triple bond. Works the same way. We're not going to add electrons, but instead we're going to take some electrons and bring them in to make the triple bond, just like we did the double bond. And now we will end up with a picture that looks something like this. And now when we look at each of the nitrogens, they actually each now have 8, 2, 4, 6, 8, and 2, 4, 6, 8 on the right. And there's still only a grand total of 10 electrons. And that is why nitrogen is actually a triple bond in this case and needs to get to a triple bond to allow both of the nitrogens basically to get to the noble gas configuration. Any questions on that? I'm going to flip the page since I'm out of room here. We'll do the last 2 on the next page here. That was NH4 and SO4. So let's take a look at these 2 guys here. NH4 plus. Again, nitrogen is 5. There are 4 hydrogens, each at 1. And here we do have a plus. So remember, when something gets a positive charge, it has lost electrons, which means in this case, we will be subtracting 1. And that will give us 8 valence electrons. Nitrogen's got to be the guy in the middle because we cannot put hydrogen in the middle. So we'll just arrange our hydrogens around. Again, we're going to do a single bond to each of these. At that point, we have now used 2, 4, 6, 8 electrons. We are good at this point. So nitrogen has 8. Each of the hydrogens have 2. It does have a charge, so we're just going to put a little bracket and a charge around it. Any questions on that one? All right, the last one that we had there was SO4 2 minus. Again, sulfur is 6. There's 4 oxygens at 6 each. Here we have a -2 charge, which means it has gained 2 electrons. So we need to add 2. That is 24, 26, 32 we'll go with. Here we have sulfur and oxygen. Again, as we saw earlier, they're in the same group. Sulfur is lower, which means it's less electronegative. And there's only 1 sulfur, which probably logically would be the guy in the middle. Everybody else is directly attached. And by the way, most of the things are like this. Everything is directly attached to the middle guy. There's no weird, like everybody's lining up this way or anything like that. You know, so usually you got a center guy and everybody's sort of attached to it. We're going to do our single bond all the way around. That is 2, 4, 6, 8 electrons. So we kind of subtract that off, do a little math. I think that's 24 left. They will go on the outside in pairs. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 at that point. I have now placed all 32 electrons, each of the oxygens 2, 4, 6, 8, the sulfur in the middle 2, 4, 6, 8. Everybody is technically good and meets the octet rule. And this would be your proper structure here. Any questions on how to draw Lewis structures? Hopefully you can kind of see it's kind of the same steps. You just want to kind of follow those steps. Any questions on any of that? Okay. All right, let's see here. So we talked a little bit about resonance structures earlier as we were just drawing these Lewis structures, but there's also something to look at, which is bond length. And you by no means need to memorize any of these numbers. But what we do see when we look at the comparison of, say, a carbon-carbon single bond to a double bond to a triple bond, the single bond is about 154 picometers in distance. When we put a double bond on, everybody comes in a little bit. The distance between the carbons gets smaller, is 133. When we put the triple bond on, everybody comes in even closer at 120. And we see that pattern even with our nitrogen here, carbon and nitrogen. Single bonds 143, 138 for a double bond, and 116 for a triple bond. So the general pattern that we see is a single bond is the longest. And as we bring those electrons in to make a double bond or even a triple bond, it brings the atoms in that bond closer and closer to each other every time you basically put another bond on. The result of that is, in terms of bond strength, we do see that a triple bond is actually stronger than a double bond, and a double bond is stronger than a single bond. And it's not like a double bond is twice as strong as a single bond or a triple bond is 3 times as strong. But the general pattern is triple bond stronger than a single bond and also stronger than double bond. I relate it usually to like a brand new pencil, right? You take a brand new pencil out of the box, it's nice and long, you could snap it, no problem. You take a couple of chemistry tests, you're left with an eraser and like a nubbin, like that big of a pencil. Very hard to try to break that pencil in half because everything's really compact and close to each other. And the same thing happens as we drop that triple bond in there. Everybody's very tight to each other and very hard to sort of break. So the relationship is longer bond, which is a single bond, is the weakest. Shorter bond, which is a triple bond, is the strongest. Now, we talked about resonance structures as we were just drawing some of those. And again, a resonance structure is usually indicated by this type of arrow. And we do, for the most part, draw these structures as we saw, like in carbonate or SO2, where really we have more than one option as to where we could do a double bond. And you could draw an equivalent structure by really just moving the double bond around to anywhere it is possible to occur. And here again was the example for carbonate. You don't have to worry about the charges. But again, we could double bond to the top, to the left, to the right. Again, as I talked about, really those double bond electrons are just moving around from one place to the next. So at any given point in time, they may be there or there or there. So we could draw 3 individual structures to sort of describe what is going on. Again, you don't have to draw all the structures unless you're asked to do so. And again, I don't think you'll be asked to do so. Benzene ring, we'll see in a later chapter as well when we talk about organic chemistry. But a benzene ring looks like this. It is all carbons here. Everywhere here is a carbon. And there's 3 double bonds. You could also move the double bonds to the other side. And most often the way we will see it a lot in our book and stuff is they'll actually just draw a little circle to indicate that those double bond can kind of move from one side to the next. Now, let's talk a little about exceptions to octet rules. And let me be really clear that everything in this class will obey the octet rule. But there are some exceptions to the octet rule that we sometimes come across, but you should never draw those in this class because we will do everything that obeys the octet rule. There are certain elements that can be very happy with less than 8 around them. And those are guys which basically have what is referred to as an incomplete octet, which basically means they're electron deficient. They're perfectly fine with less than 8 around them. And really the one that you see the most of the time is actually the guy on the bottom there. Beryllium technically, but things that contain boron. Boron is known for being perfectly fine like we see there with just 6 electrons. And it's a very common sort of arrangement for it. Again, we won't have any sort of incomplete octet in our class, but that is an exception to the octet rule. And another exception to the octet rule is an odd number of electrons. Odd number electron means like at NO or NO2, we end up with 1 unpaired electron, sometimes referred to as free radicals. Maybe you've heard of that. In chlorine chemistry or atmospheric chemistry, chlorine sometimes does that a lot. And they're very reactive because they only have 1 electron. So they're trying to fix that. So they react very quickly and stuff like that. Again, we won't see that exception here. The one that you see the most in chemistry, but not in our class, is the expanded octet. There are certain ions that can actually go over 8 electrons and be perfectly happy. And if you look at the periodic table where sulfur is to the left and to the right and down, those guys have the ability to do that because sulfur is on the 3rd period, and the 3rd period is n equals 3. And on the n equals 3 level, there are s orbitals, there are p orbitals, and they do have d orbitals available to them to basically house the extra electrons. So although they may not be using them, they have the d orbitals available to them to house those electrons, and they can sometimes go over it. So for example, SF6 is an example. You basically would have, I won't draw all the electrons on the fluorines, but sulfur is okay with 2, 4, 6, 8, 10, 12 electrons around it because it has those d orbitals and is able to do that. So for us, you just need to know what the 3 exceptions are, but everything for us will obey the octet rule. So you should always obey the octet rule in this class. But in reality, there are things that can go less than 8, and there are guys that can go more than 8. Any questions on that there? Again, we won't have any of those exceptions that you have to draw. Okay, so we're going to talk about geometry here. And we can basically use Lewis structures and the central atom to help us decide what is the sort of 3-dimensional geometry here of the molecules that we draw. And the theory that we use, or the basis of this approach, is what is sometimes referred to as the valence shell theory. And the idea is ultimately, when we make bonds, there are electrons near electrons. These guys are both negatively charged, which means they really do not want to be near each other. And what ends up happening is they cannot really escape because they're locked in the bond. So the best that they could do is try to move as far away as possible, depending on the bonds that are there, the electrons that are there, and sort of get to a place where they're like, all right, I don't really want to be near you because you're negatively charged, but I'm okay. We'll kind of keep our distance. And what ends up happening is, as those electrons and bonds are trying to move from one side to the next and get away from one another, they end up messing with the actual shape of the molecule, the molecular geometry of it. So as one thing moves in a molecule, because everything's bonded together, other things start to move with it. So we do VSEPR, which is valence shell electron pair repulsion model. And we're going to see 2 types of molecules. One where you draw the Lewis structure and there are no dots on the center atom. And that means that there's no non-bonding electrons present. And we'll see some where there are dots on the center atom. And that means that we will see some that have non-bonding electrons on the center atom. When we do geometry, it basically is all about the center atom. That is the most important one. And the most important rule to worry about for us is number 1 here. If you draw a Lewis structure and you have a double bond or you have a triple bond, we count these guys as 1 electron pair and also 1 bond. So 1 electron pair and 1 bond is what we treat double bonds and triple bonds. They're essentially thought of, even though they're double bond and triple bond and there's more electrons, is thought of as they are moving basically as 1. So that's the major important thing to keep in mind. And we do that only for when we're doing this geometry here. We double bond and triple bond basically counts as 1. Let's start with really the simplest ones to do. And if all the letters and numbers on here, don't worry too much about it. But the simplest geometry that you could have occurs from a diatomic molecule. Things like H2, F2, HF, HCl, O2, N2. No matter what happens when you have only 2 atoms present, there really is no center atom. So basically, when you only have 2 things, they are connected basically by a straight line. So when you have a diatomic molecule and you're asked, what is the geometry? The answer is linear. It's basically a straight line is the only way that you can arrange those guys. As you can see here, every single one of these that I drew, the geometry would be linear. Doesn't matter if it's 2 the same, doesn't matter if it's 2 that are different, doesn't matter if it has a double bond or a triple bond. If there is just 2 atoms present, the geometry will always be linear. The only way to arrange them basically is in a straight line opposite of each other. Any questions on that one? Now, when we get to 3 or more atoms involved, we do get a couple of different geometries that we're going to talk about. And we'll do this here. I'll just talk about what that is here. One geometry is what is referred to as the electron pair geometry or electron group geometry. That describes how the electron pairs around the central atom are arranged in 3-dimensional space. The other name for the geometry is what is known as the molecular geometry, or sometimes referred to as the shape. And that describes as a whole what the actual molecule kind of looks like in terms of its geometry and shape. So let's take a look at this one. This is beryllium chloride. This is actually an incomplete octet. Here's what we want to count. We want to go to the center atom always. We want to look, and I see 1 and 2 electron pairs. I see 1 and 2 bonds. So something with 2 electron pairs, the electron pair geometry will also be linear. Basically, those guys are going to decide I'm going as far away from each other as possible, these guys. And the molecular geometry will also be linear. It is basically a bond angle of 180 degrees. So those 2 chlorines that are bonded to the beryllium go, I do not want to be near you. I'm going to go this way. This guy is going to go this way. And they end up basically being able to spread out at opposite ends of each other and end up with an electron pair geometry of linear and basically a molecular geometry of linear, which again is 180 degrees apart. The next example is a central atom where we have 3 things attached. Again, here, the electron pair geometry and the molecular geometry. We go to the center atom. It's got 1, 2, 3 electron pairs. It also has 1, 2, 3 bonds. Something with 3 electron pairs has an electron pair geometry of trigonal planar, sometimes referred to as triangular. Because these are all bonding electrons, the molecular geometry actually ends up being the same, trigonal planar. They basically, because we have the 3rd bond in there, they could only get so far away from each other. They kind of keep some distance from each other. Because of that 3rd bond, these guys can't get a full 180 degrees apart. So they get 120 degrees apart. It's called trigonal planar because basically it makes a triangle in terms of how they arrange each other. Again, 120 degrees apart from each other.
Professor, I have a question.
Yeah.
So how do we know when they're bonding electrons?
Bonding electrons are always, the lines are when you have basically 2 dots and 2 elements on either side of it. So these guys are bonding electrons within a bond. Non-bonding electrons are the dots. So those don't have any element on the other side. Those would be non-bonding electrons. Bonding electrons are typically always the lines are, if you did this guy with dots, it is these guys here. And what distinguishes it as bonding is I see an element there and an element there on opposite sides of the electrons.
So what determines like the degree?
It's basically how far they need to get away from each other, basically. So in this particular case, what ends up happening, you know, we have these sort of fluorines here. And these bonding electrons here, here, and here really don't want to be near each other because they're all electrons. So what happens is this guy goes, I'm going to get away from you. This guy goes, I'm going to get away from you. And this guy kind of goes, I'm going to hang out here. And the result of that is the fluorine stays on top. The guys over here spread out as far as they can from each other. They can't come any further, otherwise they're going to come too close. So they want to come back. But this guy cannot swing up any higher because he doesn't want to get too close to the guy on top. So they eventually will come to a rest in a situation that is optimal for their spacing. And in this particular case, when you have 3 electron pairs and 3 bonds, the optimal arrangement is this trigonal planar or triangle type of arrangement where it's 120 degrees apart.
Okay, thank you.
Other questions? So we'll continue on here with a central atom that has 4 things attached. And that is a very badly drawn one here. Let me actually redraw it correctly here. Not sure what happened there. All right. So again, our electron pair geometry and our molecular geometry, our shape. Here we would look at the carbon in the middle. It's got 1, 2, 3, 4 electron pairs. And it also has 1, 2, 3, 4 bonds. Something with 4 electron pairs will give a shape which is referred to as tetrahedral. And basically, because we have the 4 bonds, same idea, they want to kind of keep their distance from each other. So they are going to kind of spread out in this tetrahedral arrangement. And the molecular geometry will also be tetrahedral. And it has a bond angle of about 109.5. Tetrahedral is kind of like a triangle on the sides and kind of like a pyramid shape on the bottom. And again, that is tetrahedral. Up to this point, when we look at the names of the electron pair geometry and the molecular geometry, both of the names are the same. So they're the same there, they're the same there, and they are the same there. And what all 3 of these guys share in common is when you draw the Lewis structure and you look at the central atom, there are no non-bonding electrons. So no non-bonding electrons, the dots basically. And whenever there's no non-bonding electrons on the center atom, both of these names, electron pair geometry name and the molecular geometry name will be the same always. And that's because you're only dealing with one type of electrons here, which are bonding electrons. So as the bonding electrons move, there are actual elements on the other side that move with them. When we start to introduce non-bonding electrons, we actually see a change in the two names, and the change in the name happens with just the molecular geometry name changes. And the electron pair geometry stays the same. So if we look at guys that have non-bonding electrons, we get a few different interactions that occurs. We could have bonding electrons near bonding electrons, which is okay. We could have non-bonding electrons, which are the dots or lone pairs, near bonding electrons, which is not so good. They want to get away from each other. And really the worst case scenario is when you get non-bonding electrons or lone pairs near each other. They want to definitely get as far away from each other as possible. So when we start to see non-bonding electrons on the center atom, we end up seeing different name in terms of the molecular geometry. So let's take a look at one here, which is SO2, and I think we drew it just a second ago. And if we redraw it real quick here, it will look something like this. We have our electron pair name and our molecular geometry name. We look to this sulfur. It has, in terms of electron pairs, it has one electron pair here, two electron pairs here, and three electron pairs here. Double bond count has only one electron pair. In terms of bonds, it has one bond here. And again, the double bond only counts as one. So that is two bonds. Again, the electron pairs determines the geometry of the electron pairs. And it has three, which means it is still trigonal planar. But now we have bonding electrons near bonding electrons and non-bonding electrons near bonding electrons. And again, in this situation, you have your oxygens, and they're like, I definitely don't want to be near your non-bonding electrons. So these guys are going to try to move away from each other, but they can't get too close to each other because they're also bonding. And what ends up happening is they move away into a shape which is known as angular, and it ends up being a shape that looks something like this, kind of an angular type of shape, as they move away from those non-bonding electrons as far as they can, and the overall shape ends up being angular. Some people will call this bent angular, but we will go with basically angular is a little bit less than 120 degrees, but we do see the difference here in the molecular geometry because of the presence of these non-bonding electrons. Any questions on that there? So I have two more to go, and I'm a little bit over, so I'm just going to finish these two out, and then we'll wrap it up here. So NH3 is an example here. We look at our electron pair geometry and our molecular geometry. If we look at the nitrogen, it has 1, 2, 3, 4 electron pairs. It has only the 1, 2, 3 bonds. Again, 4 electron pairs. It's the same electron pair geometry, which is tetrahedral. Again, here we have those non-bonding electrons on the nitrogen, and we have those hydrogens which decide we want to definitely get away from each other. So they end up in a shape with our non-bonding electrons up on top, which is known as trigonal pyramid. Kind of makes like a triangle and a pyramid shape on the bottom. And this is trigonal pyramid. And again, it is the presence of those non-bonding electrons near the bonding electrons, which make those hydrogens basically move, and the overall shape changes. So again, electron pair geometry name stays the same based on how many electron pairs there are. Molecular geometry does change because of the presence of the non-bonding electron pairs. The last geometry that you need to know for this class is something like water. And in water, we look at our electron pair geometry name and our molecular geometry name. We look at water, it has 1, 2, 3, 4 electron pairs around the central atom. It has 1 and 2 bonds. Again, here with 4 electron pairs, it is tetrahedral as the electron pair geometry. This guy has everything in terms of worst case scenario. It has bonding electrons near bonding electrons. It has non-bonding electrons near bonding electrons. And it has non-bonding electrons near non-bonding electrons. These two guys try to go as far away as they can from each other. The result of that is as they move out, the hydrogens basically move down, and it ends up in a shape which is referred to as bent or V-shaped. So the best way to do geometry is to sort of memorize electron pairs and bonds and the names that go with it. And here's a table similar to the one you're finding in your book. You will be responsible for only the molecular geometry name or the shape, which is like this name. So you only have to know for lecture the molecular geometry name. Again, the best way to do it is how many electron pairs, how many bonds, basically. So that's what this is basically number of electron pairs and number of bonds. Any questions on that there? All right, we will lay it up there. Thank you for hanging out. Sorry. We have just a little bit to go in chapter 6 in terms of molecular polarity, which I think is where we kind of left off. So just to finish up that chapter, then we will be going to chapter 8, which is gases. A reminder, as I mentioned, I think last week and so forth, there is chapter 7 was pre-recorded because of the exam and everything else. Just again, try to keep us on pace. So there's just 2 lectures from chapter 7 that were pre-recorded. So make sure again that you do watch them. You're responsible for them. And I think perhaps maybe during discussion this week, maybe we'll go over some of those highlights of some of the stuff that's in those lectures. But again, from here, we will be going to chapter 8. All right, so last time we finished up talking about really drawing Lewis structures. We talked about sort of geometry associated with those Lewis structures. And really the last thing in terms of bonding that we need to sort of cover from that chapter is what is known as polarity or molecular polarity. And when we talk about molecular polarity, again, this is really the last part there, chapter 6. Molecular polarity. What we're talking about is really looking at the entire molecule as a whole and trying to decide if, as a whole, overall, with all the bonds that are there in that particular molecule, is the molecule going to be polar, which means that there will be unequal sharing of electrons as a whole in the molecule. Part of the molecule will be more negative, part will be more positive. Or is the molecule as a whole non-polar, which means, again, it's essentially neutral, equal sharing of electrons. And it sort of relates to the bond polarity. If you remember, we did sort of those differences in electronegativity values. And again, we use those arrows, those bond dipole arrows. Again, it points to the more negative side, and the side that's more positive, it points that way. Remember, if it's like above 0.4, it's a polar bond. If it's below 0.4, it's a non-polar bond. Now, the easiest ones in terms of molecular polarity to decide if something is polar or non-polar are diatomic molecules. And diatomic molecules obviously only have 2 things attached. So if we look at something like we've seen before, H2 or F2, a little sketching here. And when we look at these molecules, a couple really important things. First off, We would, in this case, want to look and see if it has polar bonds. So if we look at the bond here between the hydrogen, or even between the two fluorines, we should know, based on sort of the difference in electronegativity, you'll get a difference of 0 in this particular case, which means in each of these cases, these are non-polar bonds. Now, the nice thing sort of about a diatomic molecule is when we look at the entire molecule as a whole, that is the one and only bond in that molecule, which means it makes it really simple when we look at a diatomic molecule to try to figure out, is it polar or non-polar? And it's simple because it only really has one bond, which means if this bond is non-polar, and that's the only bond in the entire molecule, either one of these guys, that means that in each of these cases, this would be a non-polar molecule, which means we would expect as a whole in each of these cases that the electrons are distributed pretty much equally over the entire sort of structure. Now, as we talked about when we're talking about sort of bond polarity, if we swap out a hydrogen for a fluorine, for example, there is definitely, when we look at this bond, this is a polar bond. And if you remember the difference in electronegativity, if we calculated it, it was something like 1.9, which is a polar bond. We could draw that arrow pointing towards the more negative side here, which is fluorine. And really for the same reasoning here, because this is a diatomic molecule and because pretty much that one polar bond is the only bond we see in the entire molecule, we can make another pretty simple guess here that this molecule here is going to be a polar molecule. And really the reason is because the one and only bond in it is polar. And what it means in this case is really the bond polarity and the molecular polarity are the same here. The fluorine side of this molecule is more negative because the electrons are going that way. The hydrogen side is more positive. So diatomic molecules are really the easiest of any of them to determine whether or not the molecule as a whole is polar or non-polar. And again, because it has only one bond, if you're able to identify that one bond as being polar, then the molecule will be polar. If you're able to identify that one and only bond in it as being non-polar, then the molecule itself would be non-polar. Any questions on diatomic molecules and polarity? By the way, if a molecule is polar, it has what is referred to as a dipole moment. So a dipole moment is represented by this arrow, and sometimes represented. In a non-polar molecule, because there's equal sharing, there is no dipole moment. There's no side that's more negative or positive, so we don't see that. Now, if everybody was that pretty straightforward, that would be great, but of course it is not. So when we get 3 or more atoms in a molecule, you really have to look at 2 things when you're trying to decide about molecular polarity. The first thing is, does it have polar bonds? So clearly, if the answer there is no, then you can pretty much stop. It's going to be a non-polar molecule. If the answer is yes, then you really need to go to number 2 here. And number 2 is you have to look at the molecular geometry. So if something has a polar bond, it may be polar, may be non-polar, but you do have to definitely look at the molecular geometry to help you decide that. And the way we do that is pretty straightforward here. Let's take a look at one. Let's take a look at CO2, which is a pretty good example. We draw the Lewis structure for CO2. It looks something like this. And in terms of bond polarity, if we use that table, you don't really even need to use the table here. If you look at the periodic table, you will see carbon, nitrogen, and oxygen. So when we're trying to decide, is it a polar bond between these two, because they are in the same period, we know it's going to be a polar bond, and oxygen is further to the right, which means it's going to be more electronegative. So we would be able to draw those bond dipole arrows heading towards the oxygen, which is more electronegative. So in terms of CO2, yes is the answer to polar bonds. So again, you may be thinking it has polar bonds, so it would definitely make sense that it is a polar molecule. And in a case like this, we do need to go to kind of the second thing here and look at the molecular geometry. And in this case, if we look at the center atom, it has 2 electron pairs. Remember, double bonds and triple bonds count as 1, and 2 bonds. So the molecular geometry of this guy is actually linear, which is a straight line. So essentially what we got going on here is we got like a straight line, and we got oxygen on one side kind of pulling. We have oxygen on the other side pulling, and I am really pulling on my pen here. And you can see my pen is really not going anywhere. And this is a very good example that you can have a molecule just like this guy here, CO2, that has polar bonds, but the actual polarity of the overall molecule is non-polar. So this would actually be a non-polar bond. I'm sorry, non-polar molecule. And that is because although there are polar bonds, they're basically going equal and opposite of each other, and they're canceling each other out. So sometimes people think about like pulling on a rope. So if you think of like 2 people pulling on a rope in a tug of war, and there's like a little like flag in the middle, and if both people pull the rope in opposite directions equally, the flag's basically going to sit there. It's not going to go one way or the other. And because they're basically canceling out each other out. And that's the same thing that's happened here. Although it does have polar bonds, they're essentially, because of the geometry, canceling one another out. And that happens whenever we have these guys here, which are really vectors. And these are vectors, which from physics means that they have direction, they have magnitude. And again, in certain cases, they can add to each other and make it bigger. And in other cases, they can cancel each other out. And cases where they cancel each other out is always when they're sort of oppositely pulling in equal and opposite directions, or even if they're pushing in equal and opposite directions. So if you think about like a swinging door that just swings, if you have 2 people on opposite sides of the door pushing equally, the door is just going to kind of sit there, right? It's not going to open, it's not going to shut, because they're canceling each other out. So CO2, a very good example that although it has polar bonds, it does not necessarily mean that the actual molecule itself will be polar. If we look at something like water, for example, water here has polar bonds. Again, the bond between oxygen and hydrogen are polar. Oxygen further to the right than hydrogen on the periodic table. So if we were to draw those arrows, they would be heading towards the oxygen here. And basically in this case, it does have polar bonds. So just like the other one, yes, we do have polar bonds. We need to look at the geometry here. That is 4 electron pairs. That is 2 bonds. That is bent or V-shaped is the geometry. So in this situation, we have more of a bent or V-shaped type of situation. We got kind of everybody heading towards the top. You can almost imagine if you had this like V and everybody was kind of going to the top, and you just pulled directly from the top, the whole thing would sort of move. And what ends up happening here is water actually does that. These 2 dipoles, because they're not equal and opposite of each other, they actually do add to one another, and they create what is known as a dipole moment. Very badly drawn there. Going through water, where the oxygen side of water is more negative and the hydrogen side of water is more positive. In case you're curious how that works, you take the guy right here and you draw it. You take the guy over here and you put it to the end of it and draw it in its direction. And then they end up adding to one another heading in this direction, which is the overall dipole moment. Again, in that case here, they're going opposites of each other. They basically subtract each other out. So in this case, because of the geometry and because it has polar bonds, water is a polar molecule where, again, there's unequal sharing of the electrons as a whole over the entire thing. And the oxygen is more negative because basically what we're saying is in the entire molecule, we have a greater amount of electrons hanging out this way than we do down here. And again, that's going to create an area in water that is more negative. And again, obviously the hydrogen being more positive. Any questions on that there? Now, most people, myself included, really don't like to draw vectors and do those things. So there should be an easier way perhaps to do it. And there is, that works pretty much most of the time. There are certain geometries which are referred to as being symmetrical geometries. And what we're talking about here are the molecular geometries. And a couple of those symmetrical geometries are trigonal planar and tetrahedral. And really what both of these guys sort of have in common, if you remember sort of what they look like, is when you draw the Lewis structure, there are no non-bonding electrons on the center atom.
Like, you know, segregated.
And if you have that sort of, please keep yourselves muted. Yes, thank you. If you if you have this situation where there's no non-bonding electrons on the center atom and everything on the outside is the same atom, this will basically lead to a very symmetrical situation where everybody is equal and opposite of each other, and it will basically be a non-polar molecule. So for example, if we draw this guy here and we look at this guy, between carbon and fluorine, fluorine is more electronegative. And we would have definitely polar bonds in this case. And they would be heading towards the fluorines. But when we look at the center atom, this is basically going to be tetrahedral geometry. All those fluorines are essentially going to be equal and opposite of each other. So like the two will pull equal and opposite. The other two will also pull equal and opposite. So I do not see any dots here. Everybody on the outside is the same. They will cancel each other out. And this will be a non-polar molecule. Now, what happens if I take one of those fluorines and replace it with a hydrogen? In this particular case, we will still have those three polar bonds. A reminder that the bond between carbon and hydrogen is non-polar, 0.4 difference. So in this particular case, by removing one of those fluorines and replacing it with hydrogen, those three fluorines on sort of this side, if you will, those guys are all pulling sort of in that direction. And we really have nobody kind of pulling back the other way. So again, if you kind of go back to the tug of war example, you kind of have like three people on one side, one person on the other side. The three people are going to be able to pull probably that one person, you know, across into the mud. And that's sort of what happens here. So we go from a non-polar molecule to a polar molecule in this case. So if you have one of these geometries and you do not see dots on the center atom, when you draw your Lewis structure, everything on the outside is the same element. It's a pretty safe bet to say that it's going to be a non-polar molecule. If you have no dots on your central atom, when you draw your Lewis structure and everybody on the outside are not the same element, then it's a pretty safe bet that it's going to be a polar molecule. Any questions on that there? So because we have some symmetrical geometries, we also have some unsymmetrical geometries. And I think what I'll do is kind of put it into here. So some unsymmetrical geometries. And again, we're looking at molecular geometries. That's your trigonal pyramid. That is your angular. That is your bent or V-shaped. And I think that's all we did in this class. And basically what all of these have in common is when you draw your Lewis structure, there are non-bonding electrons on the center atom. And if everybody is the same on the outside, it will be polar, the molecule. So for example, if we go back to here, we look at water, which is what we had here. We look at the center atom, which is, I'll redraw it over here. Center atom has dots. We have the same element on each side. It is going to be a polar molecule. So really what that leaves you in terms of molecular polarity is linear, which is a straight line, which is pretty easy. A straight line is if they go in opposite of each other, like in CO2, they will cancel each other out. If they're going towards each other, they will also cancel each other out and be nonpolar. It is possible in a linear situation that everybody is heading in the same direction. And if that is the case, then it would be a polar molecule. So that is sort of the straightforward way to do it. And pretty much you'll be okay in every of those situations. If you draw your Lewis structure, no dots, everybody on the outside is the same, going to be a nonpolar molecule. Lewis structure, no dots, everybody on the outside is different, or at least one thing is different, going to be a polar molecule. And if you draw your Lewis structure and you do have dots on the center atom and everybody on the outside is the same, going to be a polar molecule in that case. So if we look at some of the ones we drew, I think earlier on in this chapter, you know, if we look at something like this, look at something like this, look at something like this. We'll look at something like, we'll do this. Maybe we'll add. Let's see, that. I want this one too. And I think we drew this too. All right, so take a second here and decide based on what we're looking at there. Are these a polar molecule, non-polar molecule? So take a moment or two and see what you come up with. I see all of the elements on the outside are the same. That means that's an unsymmetrical geometry. That is going to be a polar molecule. I look at the center atom of the next one. I see dots. I see everybody on the outside is the same. That also is going to be an unsymmetrical geometry, and that is going to lead us to a polar molecule. I look at the central atom of this one. I do not see dots, and I see that everybody on the outside is the same element. That means that this is going to be a symmetrical geometry. And based on geometry here, this would be a non-polar molecule. Any question on those three there? This is a diatomic molecule, which means I simply need to decide, is this bond polar or non-polar? And since it is two nitrogens, I know that that bond should be a non-polar bond. And because that's the only bond in this entire molecule, this guy should also be a non-polar molecule. Coming up here to the top, we got our central atom. I see dots. I see the same element on the outside. That tells me it's unsymmetrical, and this is going to be a polar molecule. And lastly here, I see no dots. Everybody on the outside is the same. That is going to be a non-polar molecule. In addition, this molecule here has no polar bonds to begin with, as the carbon-hydrogen bond on all of those are non-polar, which means it definitely should be a non-polar. That's probably the best way to do molecular polarity. Draw a good Lewis structure, look for dots or no dots, and what's attached on the outside. Question on molecular polarity there. Okay, so as I mentioned, this is sort of some of the stuff we talked about. We do classify the molecules as polar, which again means there is a side that's more negative and a side that's more positive. And in the case here of SO2, it would be angular, and it is the oxygens here that are more negative. Sulfur is more positive in that case. Non-polar molecules have non-polar bonds and no bond dipoles. They all cancel out. Polar molecules do have that dipole moment where they really don't cancel out. And again, here's a few more examples. If we look at this, we see no dots on the central atom, but we see that all of the outside atoms are not the same. And that means that this molecule here would be a polar molecule as we see it. We see absolutely no dots. Everybody on the outside is exactly the same. They will all cancel each other out. That is our symmetrical trigonal planar geometry, our triangle. So basically everybody here is a triangle at the corners of a triangle, and they all pull equally and cancel out. This is the one we did before. I see dots. I see the same on the outside, going to be a polar molecule. Here I see no dots, but not everything on the outside is the same. And again, that now would make it a polar molecule. Again, these guys would be kind of pulling this way. These hydrogens are not doing very much to pull the opposite way. So again, if you sort of think about it like pulling a string, everybody pulls sort of in one direction, nobody really pulling back. The whole thing is going to kind of move, and it would be polar. Any questions on how to figure out molecular polarity, which is the entire molecule